Hey everybody, welcome back. As promised, we are going to solve this problem, and I'm going to go pretty quickly since you have the ability to like pause and fast forward and rewind. So I'm not gonna go through this slowly. In fact, I already have the solution written out, so we'll scroll through it quick, and this will be a quick video. So anyway, the goal is to estimate mu of the following population. So again, the population is of newborn babies in the United States, where X, any individual X represents a newborn baby's weight. Sigma X is unknown, so that's the standard deviation of the baby's weights in the United States. We don't know that. We don't know what the parent population's shape is or spread. But what we do know is that we took a sample, and in that sample, the standard deviation was 3.2 pounds. Okay, so that is something we do know, which we can use to estimate the parent population's standard deviation. We also know that the sample average weight of babies was 9.2 pounds and that our sample size was 9. Now, in general, how do I estimate a population's parameter? This parameter is a mean. In the past, we've estimated population proportions. And remember, the way we do that, the tool that we use is the confidence interval. So we're going to see here in this video how to build a confidence interval for a one sample mean. Now, the plan, again, we're building a confidence interval, so I have to state the confidence level. Let's use 95%. The procedure is going to be called a one sample T interval. One sample meaning we've obtained one sample mean, and it's a T interval because, well, we're using the T distribution now, not the Z distribution. So we're building a T interval. Now, what's important, what's going to be useful in our calculations? Well, X bar, of course, right? A confidence interval is always centered at your sample. In this case, the sample statistic that we're interested in is the mean, and that was 9.2 pounds. Excuse me. So moving on, standard deviation of the sample was 3.2 pounds, as I mentioned earlier. That's going to come in handy. Another thing we have to worry about when we're using the T distribution is this thing called degrees of freedom. And when we're dealing with one sample, the degrees of freedom is simply equal to the sample size minus 1. So our degrees of freedom are going to be 8. Sample size itself, again, is 9. And the parameter we're trying to estimate is mu. It is the average birth weight of all U.S. newborns. Okay, so that's our plan. Now let's make sure that we're allowed to use the T distribution. So in the next couple of minutes, you're going to see like what are the necessary conditions to be met, and I'll discuss briefly how to check those conditions. All right, but obviously the more examples we do, the more ways you'll see of basically how do we check these conditions. You'll recognize these conditions. They're not different at all. So justify random sample. Well, I didn't really give too much information in this problem, so we don't know if the sample was random, so we're going to proceed with caution. 10% condition, well, 9 is definitely less than 10% of US newborns. And then the last condition we have to worry about is something called the nearly normal condition. Now, if the sample size is greater than 30, we're good to go. And that's really all we would have to check. But in this case, sample size is not greater than 30. And if that's the case, then we want to check, does the sample that we obtain, so in this case, the 9 babies, are those weights in the sample distributed normally? Well, again, I didn't really list out the individual data points, so I can't even check to see if those 9 weights look to be distributed normally. How would I check? Well, I would use a normal probability plot, plug the data into the normal probability plot, and see if that normal probability plot implies something about normalcy. And If you don't remember how to do that, that's okay. We will definitely go over examples at some point later on down the road. But anyway, so we don't really have the means to check the nearly normal condition in this situation. So again, I'm going to say unknown and proceed with caution. All right, so kind of weak justification there. In reality, you'd be given a lot more information to be able to check these conditions. All right, but now let's assume the conditions are met. If so, then we have shown that X bar is going to be distributed using the T distribution. And notice I have a subscript there. Remember in the previous video that T distribution changes as sample size changes. And well, as sample size changes, degrees of freedom changes. So it's not enough just to say that X bar is distributed T, but it's distributed T with a certain subscript. And in this case, the subscript is 8 because that subscript refers to the degrees of freedom. All right, so keep that in mind, that when you list your distribution using a T distribution, the subscript refers to the degrees of freedom. Now, the parameters are going to be the same as always. That is that our mean, the center of the distribution will be mu, and the standard deviation, the standard error of this distribution is going to be 3.2 over radical 9. Now notice that that 3.2, that is the sample standard deviation, and we're using that as an approximation for the population standard deviation. Also, I left the mean as mu because we don't know what mu is. We're not making any assumptions about it. There's no like null hypothesis or anything. That's just simply the value that we're trying to approximate here. So that's why mu, the center of this distribution, is left as mu. All right, moving on. My 95% confidence interval is going to be found just like you're used to. I'm going to take my sample statistic and then plus or minus the critical value times the standard error. The only difference here is the critical value is going to be some T star. Well, let's go into how we calculate that. So again, 9.2 plus or minus. So the T star, in order to calculate that, you're going to use, instead of inverse norm, you're going to use inverse T. So you should be able to find that function on your calculator. Although actually I believe some of you don't have that. And what you will need to do is go into your textbook and use the T table. So if you do not have the inverse T function, please message me on Google Classroom and I'll tell you where to find the T table if you can't find it. And I'll show you how to use it. All right, so that's something that we'll address on a case-by-case basis. So anyway, you would use inverse T. You type in 0.975 because remember, if we're 95% confident, then that means 95% of the information is in the middle and 5% is in the 5% total is in each tail, which means 2.5% is in the upper tail. So that T star is actually the 97.5th percentile. And the other piece of information you have to input into inverse T is the degrees of freedom. You have to tell the calculator which T distribution you're using. Okay, so that's something that's important to know. Standard error, of course, is just 3.2 over radical 9. And adding and subtracting these numbers, we get a lower bound of 6.7403 and an upper bound of 11.6597. Of course, those are in pounds. And the summary, I typed this up just to save you from brutal handwriting. And we can summarize this result by saying we are 95% confident that the true average weight of US newborns is somewhere between 6.7403 pounds and 11.6597 pounds. And there you have it. All right, ladies and gentlemen, that is going to be all for this video. If you have any questions, please let me know. Please show up at SGI if you need anything. And hope all is well. And I will talk to you next time. Take it easy.